My name is Russell Kennedy, and I am presenting Self-Organizing List. A self-organizing list is a list data structure that reorders itself based on element access. It does so by rearranging elements based on how frequently they are accessed. The goal of this structure is to improve average access time over usage of the structure, and the simplest implementation is as a linked list. There are four methods of implementing a self-organizing list. The first two, move to front and transposition method, were the original two designed by John McCabe in 1965 with the original algorithm for a self-organizing list. The other two, count and ordering method, were devised by future computer scientists in an effort to improve on the existing algorithm. The move to front method moves any accessed or searched element to the front or head of the list. Additionally, it does not require any extra memory. Similarly, the transposition or transpose method does not require any extra memory, but rather than move any accessed or searched element to the front of the list, it merely swaps it with its predecessor in the list. Over time, any elements that are overly accessed will be swapped until they are close to the front. Next is the count method, which adds a variable count to each element. This variable is incremented whenever the element is accessed or searched for, and the list is rearranged by decreasing count order. The last method, deemed ordering, differs from the other three. It is the only one to have a rule establish an insertion rather than access or search. Whenever an element is to be inserted into a self-organizing list with this method, it will be inserted in the most appropriate spot based on established rules. For example, inserting a value 2 fits perfectly between the values 1 and 3 in this example. Now, the worst case time complexity for a linked list implementation is the same as a base linked list, with the exception of the order method. The worst case insertion for that would be O of n, due to the fact that with order, if a value is deemed to belong at the end of the list, it will have to increment through the entire list. The average time complexity for search and access in this structure could be described by the equation T of n equals 1 times P of 1 plus 2 times P and 2, and so on, where P is the probability of that element being selected. And the best case time complexity for search and access would be constant, whereas the element we're searching for is at the front or head of the list. Applications of self-organizing lists can be seen in language translators which utilize the algorithm to maintain symbol tables. It can also be seen in AI development, neural networks, and other algorithms like least frequently used. Overall, the self-organizing list is a sound structure for handling patterns and can be applied to a good range of problems given its different methods of structure.